up to this point, we've talked about what a hash table is. We've talked about a hash function, what that is. So now I'm going to be moving on to talking about collision resolution, because that was one key scenario that we have not yet talked about, is what happens when a hash function gives us the same position for two keys of two different records. So keep in mind, they're two different records. They don't have the same key, but they hash to the same position. So that's what we're going to talk about now. Is we're going to focus in on how do we resolve collisions, or at least how do we not necessarily we're not trying to make it so that we cannot have collisions. I'm trying to resolve the issue of what do we do when a collision occurs. So I'm not giving you ways here to talk about how we ultimately get rid of them. That's a whole other matter altogether. We're going to talk about not separate collision, but separate chaining. So let's talk about separate chaining. This is the first one we're going to start with. So the solution here is rather straightforward. So I'm going to give you a demonstration for how separate chaining is going to resolve the issue of a collision. So suppose I have my friends, and say my friends are going to the movie theater. So say I have my friend, say it's my lovely, lovely plushy friend. I got my lovely giraffe friend. I got my lovely sleepy friend. My friend's a little sleepy here. And I got my friend that likes a lot of water. So suppose that my friend here really wanted to get to their spot as early as possible because they didn't want to dry out, and say there was a nice pool at the bottom. And say they were told to, hey, come sit right here. So come sit right there. So there's our friend right there in that spot. However, suppose that, say my other friend, my giraffe friend, really wanted this spot. Now, if we wanted to tell our seal friend to move, well, that would be one way to resolve this conflict, this collision of preferences, right? Well, what do we do here? Well, now there's a lot of ways we can go about this. For here, in separate chaining, the way this is going to get resolved is the two are going to share the exact same spot. So what's going to happen is they're both going to go into the exact same slot, or the exact same seat. So naturally, this being a theater, they're going to be starting to sit on top of each other. So when, say, my sleepy friend comes along and say, hey, look, I want, and say there's a collision that happens here, they're gonna come sit there. Then say my very plushy friend, who's very nice, very friendly, is gonna come sit on them. So the idea here is that whenever there's a collision, we're going to use more memory to store them at that slot by using a secondary data structure. So the idea is very simple. If a collision occurs, you just simply use more memory. That's all you do. So I'm going to show you a classic way of going about this. So in separate chaining, you can treat each entry or slot of the table, of table T, as a linked list. You can have a linked list at each one of the spots, akin to the explanation I gave you near the beginning with node references or pointers. So, for example, if I want to get the data with a given key, I would need to, it'll be in one of the lists in this table. So to get data with key K, hash using H of K, the data will be in T sub H of K. So you'll use this result to tell you where it is, but it will be in one of the lists. So I thought it'd be a good idea I do an example just to show you what I mean. So let's do an example. So suppose that I have a hash table and it has 7 slots in it. 1, 2, 3, 4, 5. So I have 1, 2, 3, 4, 5, 6, 7. Let's say this is my table T. It's my table T. And it's going to have 7 slots in it. And suppose that I have these following records. 21 V1, 13 V2, 12 V3, 7 V4, 3 V5. And suppose the hash function is as follows. H given K is K mod 7. Notice that the 7 here matches up with the table size. So notice that because they're numbers, it's much simpler to do. So anyways, what we're going to do is we're going to insert or perform put operations on this hash table using the idea we just talked about here. So this will hopefully clarify what we have to do. So if I have 21, I would give 21 mod 7. Now 21 is the same as 7 times 3, right? Because 7 times 2 is 14, plus 7 to that is 21. That means that it cleanly divides 7, meaning that it has no remainder. So what I do is I create a new node, and I'm going to insert it at the head of this linked list. So each one of these is going to be null at this point. Then, so far I've inserted in 21. If I want to access 21, all I have to do is put 21 in here. It tells me to go to position 0, and I will just traverse this linked list until I see 21 as a key. If it exists, it will be in this list. If it doesn't exist, it will not be in this list. Why? Because if it was in fact that key, the hash function would have given me that position, right? So next we have 13. Now 13 is 1 less than 14. And we know 14 mod 7 would be 0, so that means it's going to be 1 less than that. But remember, you got to think of it like you're wrapping around like this. So 1 less than 14, if 14 puts you right here, then 13 puts you here. You got to think of it like wrap around. It's wrapping around like this. So 13 V2. And just for the sake of clarity, I should make sure I put my second attribute for the node. So this will be nil or null at this time. So far we got 13. How about 12? Well, 12 is 1 less than 13, so it's going to go in position 5. Okay, now 7. Now 7 is just going to divide 7, right? So that means that it's just going to go right up here. So I insert this at the end of the linked list. Now remember, I cannot just simply put it at the front and end of the day, right? I can't just do that. I have to make sure there's no duplicates, right? So that means I have to traverse this linked list in the worst case. It's going to go through all of them. So I have 7, V4, and this becomes nil again. And last we have 3. So 3 goes in 3 because 3 mod 7 is 3. And there we go. We did a whole bunch of insertions on the hash table using the separate chaining approach. So notice all we do is whenever we have a collision, we're going to just simply, so we'll look in this list. But if ever we have to do an insertion, we check the list to see if it's already existing in that list. If it doesn't exist, I insert it at the end of the linked list. Now keep in mind, once you've checked for duplicates, it doesn't matter if it's at the end or at the beginning. But since if you're traversing through the linked list anyway, from the front to the back or rear, you may as well just put it at the rear because you already have access to that pointer or reference. Doesn't make much of a big difference. at least from a time complexity standpoint. So I must stress that doing the insertions and removals is not any different than really doing insertions and removals on a linked list, as I talked about at the beginning of the session. So all you'd have to do is just traverse the linked list, do the insertion if you don't have a duplicate. Do the removal, you just find that record in that given list, and you just perform the removal from a linked list. It's no different. So I must stress that the algorithms for put and remove are similar to inserting and removing a node in a linked list. And I must stress that this is where you have to preserve the fact that you can't have duplicate keys. So just remember that. So I must stress that the analysis that we're going to discuss here is not going to be much different otherwise. So I thought it'd be a good idea I give you the pseudocode for get, so that way you can see what one of these would look like as pseudocode. So we went through the process, but it's important that you see it at least once. Okay, so we're going to have algorithm. So I'll write out the algorithm based on what we just discussed, and then we're going to analyze it. This time I'll do it a little bit more carefully. Algorithm, it's going to have get, it takes in a key, input, takes in key k, output, it gives us the data for key k, and null if k is not in capital T, the table. So it returns null otherwise. So first, we're going to get a position. So what we're going to do is we're going to go, so actually I want to know I want to get the pointer, hence why I'm going to use a P, for the given slot or position in the hash table. So what I'm going to do is I'm going to get the appropriate list using the hash function. So I compute this position, I index into the hash table to get the pointer or reference, depending on which language you're talking about, to the head of the linked list that where this record should be, if it exists. Then next, while p is not equal to null, and if I get the key from this node, because remember this is a pointer or reference to a node, if I get the key at that node, if it's not equal to k, if both of these are in fact the case, what can I say? If it's both, that it's not null and it's not the key. Wow, that's very natural. That means I just need to keep exploring the list, right? If it becomes null, then it means I've explored the entire list and I didn't find it, right? If it becomes equal to k, then I found the record in one of the nodes in that given list, right? So for both of these to be true means I still have to keep exploring my linked list. I have to continue to my traversal. So I'm going to assign P to be the next node in the linked list by getting its next attribute. Now, like I said, there's only two possibilities now. It's either this is going to get falsified or this is going to get falsified. You can't have both of these happen at the exact same time. And also do take note, by the way, of the ordering of these two conditions. I'm taking advantage of the concept of short circuiting. So I'm checking if it is null before I check its key. It's a very important distinction. Because if this happens to become null, then I can't get its key, right? It doesn't make any sense. So if P is equal to null, then surely it doesn't exist because we did not find one with a key that matched it. Otherwise, I can return the data from that record. Else, I can just return the data of the given record. P.getData. Piece of cake, right? So if there are any questions about this, don't hesitate to stop me, okay? Okay, so let's go through the analysis here. So I'm just going to number these lines just to make this a little easier for us to see what's going on. So let's talk about each one of the lines. Now, I would encourage you to write this out more carefully in words. So I'm just going to give you an overview of how I would compute the time complexity of this. So one major thing is that in the worst case scenario, you may have to explore this whole list, right? So just keep that in the back of your mind. So let's look at our time complexity. So the analysis is as follows. So if I look at line 1, this takes some constant amount of time. So suppose it's C1, so it's constant amount of time, because computing the hash function in our case, I'm just going to presume it's big O of 1, and accessing that given spot to get the reference to the head of the linked list, that takes constant time. If not, you can just presume it's big O of k. But either way, you get my point. Next for line 2. Okay. Let's look at line 3 first before we get to line 2. So like I said, I recommend you break this into sentences. So I'm just doing an abridged version here. In my notes, I have a much more comprehensive explanation here in words. So I encourage you to think about how you'd reason this out. So C3, getting the next node in the linked list takes constant time. So I'm going to call it C2. It takes C2 time or C2 many operations. Now, what else can we say? Well, see, lines 4 and 5, both of them take some constant memory or number of operations, right? So I'm just going to say that takes C3 time or operations or C3 operations. It's either way, these are all some simple operations. They're combinations or compositions of simple operations. That brings us to line 2. Now, line 2 is a while loop, and in the worst case, you're going to have to go through this until this gets invalidated, right? Until this becomes null. So if that is the case, when p is equal to null, that means you had to go through the whole list. So that means that if you take line 3 in combination with line 2, if you take line 2 with line 3, it performs iterations based on the length of the list, right? So let's put this all together in a complexity function. So the running time should take a form that looks kind of like this. Well, specifically with the way we derived it, it'll look like this. So this is our complexity function. C1 plus C3 plus C2, because remember, I just have C2 right here anyways. So it doesn't make much of a difference if I just leave it out to its side, but really it's 2 with 3 together. It's 1, 4, and 5, and 2 with 3, right? So it's C2 times the length of the list, right? So if you put this all together now, what can you say about the big O here? Well, we have constant, C2 times something that may not necessarily be a constant. So in the worst case, there's a possibility that your hash function, with a bad hash function, or just simply in the worst case, what it can happen is it can actually hash all of your records to the exact same list, or even half of them, for example. But you can get, there is a way you can build a hash, such a hash function. It's very simple, believe it or not. For example, and say my earlier example where I had the hash table with size with the length of 7. Suppose that every one of my records was a multiple of 7 for its key. So it was like 7, 14, 21, and so on. All of those would index or tell me to hash to position 0 in the table, meaning that all of them end up in that table slot. So in the worst case, you can have this happen with a bad hash function, or just in the worst case, just generally. It's big O of n, where n is the number of records in the table. So this is your worst case. So, however, with a good hash function, meaning the one that satisfies my uniformity assumption that I talked about and the things we discussed, it's big O of 1 on average. Presuming that always the number of records is going to be is never going to exceed the size of the table. So hopefully that is clear. So if you might ask about this, well, remember, if the keys are uniformly spread across the table, like almost like I take a bagel out and I took a butter knife and I spread them uniformly across there, the way this would behave on average is you can imagine it like if they're uniformly spread, meaning that when I access them afterwards, you can almost imagine this just as you would expect it to behave that I get very few collisions, so some constant number. It's like if it were to perfectly know where to go, but this is, remember, like I said, average case behavior. And I must stress, the fact that it's big O of 1 with a good hash function, that should tell you on average that this practice works rather well. So I have more to say about what this means on average for separate chaining here in a moment. But yeah, so in the worst case, you get big O of n. On average, it's big O of 1 with a good hash function. As good hash function, meaning it satisfies our uniformity assumption. I'm not going to tell you why, like as with a proof, but I think the intuition should hopefully be helpful enough. But I'm going to extend on this to talk a little bit more about the practice of figuring out how you would go about this. So I want to talk about another concept. So actually, before that, let me just summarize one quick thing. So just to make sure it's clear. So if you talk about get, put, and remove, all of them share this property, that the worst case is big O of n, the average case with a good hash function is big O of 1. So just be aware of this. Now, there's an underlying and important thing that I have not talked about with, hey, get back here, camera, get back here. I have not yet talked about when it comes to separate chaining, is that because you can keep adding in more records, even more than there are slots, in separate chaining, you get the unique opportunity that you can actually have it where there's more records than there are table slots. So that means that I want to also talk about how the average case behaves when you have it where you have more records than table slots, which is something that you can do with separate chaining. So I'm going to define something called a load factor. This is an important hashing concept. Very often the load factor helps dictate which hashing approach you might take depending on the table size. So this load factor often plays a role in practice for how you might pick the table size. All it is it's some number where it's the ratio of n, the number of records or things you have in your table, over the number of slots. So previously we've assumed that n is less than or equal to capital M, right? However, I'll say semicolon, spice this up. However, in separate chaining, I'll abbreviate it with SC just for the sake of brevity. We can have n strictly bigger than capital M. So you might ask, Dan, how would this behave on average then if you have it where you can have more records than there are slots? I like to use the analogy of a cake with layers, so a layered cake. So suppose that the load factor first was based on the explanation I gave you earlier, or intuition. It better be put as an intuition, because I didn't give you a proof for it. If the load factor was strictly less than 1, meaning that you have, it's less than or equal to 1, that would mean that there's no more than the table slot many records, right? So the intuition would be that if your load factor says about 1, that you should expect it to be that when you put things in here, that it'll go here, then it might go over here, then it might go over here, then it might go over here, it might go over here. The point is it fills up the first layer. That's the intuition behind it. Now, I must stress that this is just a helpful intuition. However, as soon as I have more records than table slots, the load factor now plays more of a role, and the load factor actually dictates how many layers you're going to have for your cake. So for example, if the load factor was say in this case, it was like 4, you may have 4 layers to the cake. And for each one, if they're uniformly spread across the key, the keys are uniformly spread like this, then you should expect it to act this way for each one of the layers. At least that's the statistical intuition behind this. So you might ask, okay, so what is this then? Well, surely it can't be more than just slightly beyond this, and the fact that the load factor can be less than 1. We have to account for this. So notice that on average, instead of it just being big O of 1, it's going to be big O of 1 plus alpha, where alpha is the load factor. So notice that if you keep alpha relatively small or constant, it's going to just still be big O of 1. That's the big thing I really want you to notice. So you might say that the time to traverse the list on average is this. So here's a practice that you can use to make sure that big O of 1 plus alpha stays big O of 1. If the number of slots is proportional to the number of elements in the table, number of elements or records, in the table by some constant, then what does that mean? Then if I look at alpha, then it's n over m. But if these only differ by some constant, so by some multiplicative constant, then this is big O of 1. So you might say, Dan, what should the table size look like? Well, keep this practice in mind. If you find yourself having it where the performance starts degrading, what I recommend is and keep in mind that the load factor exceeds the constant value you've chosen, then that means that you should increase the size of the table to another constant that you're familiar with or think would be appropriate for the design of your hash table, and you would rehash the entire table. I must stress that rehashing the table is very expensive to do, especially if you have many records in it. I mean, tens of thousands at minimum. Like, so just keep in mind this practice. This will ensure that 1 plus alpha is in fact going to remain big O of 1. That alpha doesn't get out of control. So that's all I have to say about separate chaining. Hopefully you found that. Actually, no, I have actually one interesting remark I wanted to make. So one other remark I wanted to make about separate chaining is that you notice that in our representation for separate chaining, we use linked lists. This is because the keys don't necessarily satisfy total ordering. So we have to keep our approach rather general, akin to studying, say, a linked list that stores records in an unsorted manner. Now, if you have additional information, such as if the keys maintain a total ordering, meaning that you can list the keys from smallest to largest, or arrange them in this manner, well, here's the neat thing you can do. You can actually speed up the operations that we've been talking about. So in the special case, when you can implement an ordered dictionary as opposed to just any old dictionary or map, what you can do is you can actually specialize the secondary data structure. So instead of having a linked list, you can replace it, say, with a self-balancing tree, or some other concept where say, for example, this is something that I do eventually talk about, is a concept called an AVL tree. There's another thing called a red-black tree. These are self-balancing trees that are able to perform operations such as searching, insertion, and removal in big O of log n time. So you notice how my worst case here was big O of n. In the specialized environment, what you can do is you can actually make it so that all of our get, put, and remove operations for an ordered dictionary can be improved to big O of log n as opposed to big O of n. This is because of the time complexities of that data structure. So you can modify the data structure for your more specialized cases. That's why I said more broadly that whenever we have a collision, we just use more memory. If we have more assumptions in play for how we can do this, the secondary data structure can be better tailored for the scenario. So hopefully you found that interesting. One remark I will make about that is that in that specific case, actually some later versions of Java, the more recent ones, at least to the date of this lecture, actually do use this approach. So what they do is for shorter lists, so for a shorter number of collisions that occur in a given list, it uses the approach we talked about here with linked lists. But as soon as they start getting longer, what it does is it converts it into a red-black tree. So it treeifies the list, and it'll start behaving like this. And you might ask, Dan, why doesn't it just do the tree thing from the beginning? It's because having around those extra pointers is storage that you're using. There's space you're using. From a big O perspective, it doesn't change anything. Just the thing is, in practice, it might. But yeah, rather interesting, right?